Hi and welcome to the Neil Ashton podcast. In each episode, we explain some of the fascinating ways that science and engineering are changing the world around us. We talk to leading engineers from elite level sports like cycling and Formula One, to some of the world's top academics to understand how fluid dynamics, machine learning, supercomputing are bringing in a new era of discovery. We also hear some of their life stories, their career advice, and lessons they've learned on the way that I hope will be helpful to you too. So sit back and enjoy this episode. Hi and welcome back to the Neil Ashton podcast. So today's guest is Professor Russ Cummings. He is the director of the Hypersonic Vehicle Simulation Institute as part of the United States Air Force Academy and has had an amazing career over the past 40 years. He turns 70 later this year. And he's well known for, well, actually many things. He has one of the most popular textbooks, Aerodynamics for Engineers. There's a new version coming out this year, or it's just come out, which we talk about briefly. But he's had this amazing career where he's gone from being, in academia, he went into industry, he was then a professor for a long time. He's been key in terms of collaborations with the rest of the world. Notably, we talk about his links with Oxford. And I got to, know of his work more recently through the United States Air Force Academy and his work in terms of leading the resurgence, of research into hypersonics CFD, something that is very topical and very challenging. And so we go through his motivations, his early days at university in California. We talk about him going into industry. We spend some time dwelling, which I really love, the time at NASA Ames. This is a bit of a common theme in a lot of the people I interview. They've often been there. Some of his overlap with some key figures. I will try and post a picture, if I can, on YouTube in the comments, because there was a picture that he shared of 50 years of NASA Ames, and I think he was in that photo on the field there. And yeah, so he interacted with a lot of people, with Mike Giles, who's in this season of the podcast. Talks about the great time coming over to Oxford. Like I said, the college environment, collaborating people, the difference in working habits between the UK and the US. Some funny stories along that. And then towards the latter part of the episode, we talk more about hypersonics in particular and some of the challenges compared to low speed, some of the cyclical nature of funding, and really how I have observed him to really have changed that to some extent and pioneered and pushed for a renewed focus on hypersonics research for CFD. I got to know him partially through that, through the program that he runs with the DoD High Performance Computing Modernization Program, this HVSI that we talk about, which is combining experimental and computational research, applied research, to solve some of the great challenges of hypersonic CFD. So we talk a little bit through that, and then we go towards the end, really advice that he has for people. And he's very inspiring figure, actually. Somebody's very easy to get along with. You see him at the AIAA and conferences like that, and he is really genuinely, I think, being an influential person in the community that is someone I personally, really do look up to. Now, we should say that because of his role, we wanted to make sure that there were certain things that people understand in terms of, just his opinion, essentially. So I did want to, I put a little note in the YouTube comments around what can be said, but I wanted to just read out a little bit of a disclaimer, because we don't want to get in trouble. So basically the disclaimer is that the views expressed in this interview are those of the author and do not necessarily reflect the official policy or position of the United States Air Force Academy, the Air Force, the Department of Defense, or the US government. So it's just his opinion, and I thought it was a very good and very interesting opinion, and I hope you fine too. So please sit back and enjoy this episode with Professor Russ Cummings. Yeah, well, firstly, thank you very much for coming to talk. You know, your name is synonymous with CFD and aerodynamics. Everybody knows who you are, but I still think maybe not everybody knows your full sort of story and your opinions on things. So it's, great opportunity to speak to you. So thank you very much. And you've had an amazing career spanning, decades with so many notable achievements. But maybe we could start by winding back the clock a little bit to your early motivations, aspirations. Did you always want to be an engineer when you were growing up?
Yeah. So, well, first, thanks for having me, Neil. It's great to see you, and it's great to have this opportunity. So the quick answer to your question is, did I always want to be an engineer? Is no. I grew up in Santa Cruz, California, which is almost like a resort community about 70 miles south of San Francisco, right on the coast. So beaches, mountains with redwood forests, nice. Wonderful place to live and grow up. And I was taking full advantage of that. I was a very busy kid with sports, mainly baseball, and Boy Scouts and church and music and all kinds of activities. None of them specifically about airplanes. And so that was not there, and certainly not, I wasn't, there were kids in my neighborhood who grew up tinkering with cars, making go-karts and things like that. That wasn't me. I just wasn't that kid until I reached the ripe old age of 12. My uncle was a master sergeant in the Air Force. And I'm going to date myself here now. He was on his way to serve a tour in Vietnam during the Vietnam War. So this is in the late 1960s. So now you can put it together. How old is this guy? I was 12. He decided on his way, he was going to Da Nang. On his way there, he was going to stop and visit us. He was stationed in Ohio, and his family was in Ohio near Columbus. And he decided to come see us on the way for a couple of weeks, since he was going to have to fly, I think, to Travis Air Force Base, which is in the San Francisco Bay Area, and then from Travis to, eventually to Vietnam. So he came to visit, and he started almost immediately going down with me to the local hobby shop and buying models of Air Force fighters. And at that time, that was like the Century series of fighters, and then into the F4, so the F-100, the F-102, the F-103, the F-104, the F-105. And every day, it felt like, while he was there, he would buy a model, and we would sit on the kitchen table at night and build those models together. Wow. And he would tell me stories about those airplanes. And it was just like a light went off. I want to do something related to airplanes. That has been there ever since. It's interesting, when I worked, my first job was at Hughes Aircraft Company in Los Angeles, and we can talk about that more later. But everybody I worked with in the aerodynamic design department loved airplanes. That was the common thread. Yeah. It wasn't that I knew how to fix engines. It wasn't that I grew up doing one thing or the other. It was, there's something about airplanes that I just love. And that bug hit me when I was 12 because of my uncle. And so even though he then eventually had to leave, those airplanes started finding their ways onto the ceiling of my bedroom. And every night I would look up at them. And now my bedroom ceiling was pretty full of airplanes. There were many airplanes that we'd built models for. And I knew I wanted to do something related to that. Probably initially to be a pilot, but not completely sure. That kind of shifted slowly, kind of evolved as I went through middle school and high school. We called it junior high. Some places in the U.S. they call it middle school. And then through high school, I had some good advice from high school teachers, math and science teachers, who told me, well, if you want to be a pilot or you want to do something related to engineering, you better be taking all the math and science courses you can. So I signed up and made sure I was enrolled in what we called college prep. So the track that was going to lead you to go to university. And then spent time thinking about where that would lead me, which university I would go to. There were many options for that in California, certainly. I also looked out of state, so places like Purdue and the University of Colorado at Boulder. But primarily, so that I wouldn't break my parents' piggy bank, I chose to go to Cal Poly because it was in-state, very low tuition, and very, very affordable. It was also a 3-hour drive away, which I thought was the perfect distance.
Not too close.
If you were closer than that, your parents could just show up for lunch. But if you were farther than that, it was harder to go home on a weekend and do your laundry, right? So I thought 3 hours was perfect. So that's about 3 hours south of Santa Cruz in San Luis Obispo. Again, on the coast in a beautiful place. And Cal Poly was just the perfect place to go. Cal Poly's motto is to learn by doing. They're very big on a hands-on education. So it was like with every course, with every topic, there were lab experiences, if not outright full laboratory courses. So we had a hangar and an airstrip on campus at that time.
Oh, wow.
For example, at one point when I was a senior, Burt Rutan flew one of his aircraft in from Mojave and just landed it there and came and talked to the AIAA student branch and then flew out again. So it was pretty exciting to be there, to be learning about aeronautical engineering. And at that time then, the pilot evolution kind of concluded. And I realized I want to be an engineer. That happened sometime in my first or second year at the university, where I shifted from I want to be a pilot to I want to be an engineer. I went to school with many kids who became pilots. So that was definitely a possibility. Probably a third of my graduating class in aeronautical engineering at Cal Poly became pilots. In fact, I just saw some of them recently, and now they're retired pilots, but their careers spanned many decades of first flying for local regional airliners. Many have went back in the deregulation days, went bankrupt, and then they got a job at another one, and it went bankrupt. And eventually they caught on with one that got bought up by a larger airline, which started to happen like in the 1980s. And they all eventually became pilots for American or United or Delta, the big U.S. airlines. And then spent the rest of their career flying around the world. So that certainly was an option, but the engineering part of it was what started to attract me. And maybe one of the clinchers was during the junior year, we had our first course in aerodynamics, which, perfect. Didn't know that's what I wanted to do. I still wasn't sure, all these topics, structures and propulsion and aerodynamics and design, etc. Which thing are you going to spend your career doing? I wasn't sure, but I knew one thing. While most of the teachers at Cal Poly were pretty good, the guy who taught us aerodynamics it wasn't that he didn't know it. He knew it. He had this philosophical belief that it was his responsibility to make you figure everything out and not for him to teach it to you. I hope when I teach that it's a little bit of both, right? I'm explaining and you're trying to absorb and learn. He wasn't that way at all. And so I remember coming out of our classroom one day with these other students and saying, I could teach this better than him, and I don't even know the subject matter. I could just read ahead in the book and do a better job. And little did I know, it was kind of prophetic that I was going to spend my entire career doing aerodynamics. I just didn't know that at the time. So Cal Poly was a perfect place for me. I then stayed there and got my master's degree. And then did the worst thing that, as I was growing up, that I could ever imagine doing, and that was to moving to Los Angeles to get a job, because I grew up in Northern California. And for those of you in the rest of the world, you might not know this, but there is a fairly intense rivalry between Northern California and Southern California that plays out in sports. For example, I grew up a San Francisco Giants baseball fan. We were trained from a very young age to hate the Los Angeles Dodgers. Okay. And in fact, forget just the Dodgers, hate anything to do with Los Angeles. Wow. So moving to LA to go to work was almost like a sin. You just couldn't believe what people thought of me. What are you doing moving to Los Angeles? It's like you're moving to the enemy's territory. And so I moved to LA and to start work at Hughes Aircraft Company. Now, it was interesting. When I started at Cal Poly, everybody, and I mean everybody, told me I was making the biggest mistake of my life. Not because I was going to Cal Poly, but because I was majoring in aeronautical engineering. And that was because of the timing. I started at Cal Poly as a freshman in 1973. That's the wind down of the Vietnam War, the wind down of the defense industry's kind of golden era, you could say, and also a number of other factors. There was the oil crisis in 1973, and so oil prices shot up, and gas prices therefore shot up. And so people were just telling me that I was making the worst decision of my life in enrolling in aeronautical engineering. I didn't care. It was the airplane thing, right? It didn't matter. It was the airplane thing. And so by the time I graduated, so that's 77, I couldn't have made a better choice because nobody was majoring in aeronautical engineering then, relatively speaking. And now, by the late 70s, defense and aerospace industry is ramping back up. And I literally had people just throwing job offers at me as I graduated. I had about 9 job offers.
Wow.
From all the companies you could imagine you get job offers from government labs, from the Navy, from the Army, whatever. I'll never forget the offer I got from Boeing was to work in the group doing the Boeing 767 wing loads and flutter, which that's pretty cool, right? Yet I didn't take that job because of the job offer I got from Hughes Aircraft Company, which was to be a missile aerodynamicist. Not for one missile, not for one part of one missile, like the offer I got from other companies, like one airplane, one part of one airplane, one thing about one part of one airplane. And then you wonder, well, what happens when that's over? What happens next? I wanted to be somewhere where I was going to learn as much as I could about aerodynamics and more than that. It was the perfect place. Hughes was a unique aerospace defense contractor, to put it mildly. Howard Hughes wholly owned the company back in the 30s, the 40s, the 50s, and then eventually donated the company to the Howard Hughes Medical Institute, which he controlled. It took the government decades to prove that that was illegal, but it didn't matter. While I was there, and of course Howard Hughes had passed away, but we were a nonprofit defense contractor, which that doesn't make sense. Right? Hughes was known among the other aerospace companies as the country club of the aerospace industry. That wasn't true. We did not have hot tubs in our buildings, as some people thought. But it was very flexible. It was very open. Hughes had, you could sense this from the people who had been there since the days of Howard Hughes. When it was time to work, you worked. If that meant you went on a wind tunnel test in Tullahoma, Tennessee, out in the middle of what felt like nowhere at the time, and had to be there for weeks, even possibly months, and at times working 2 or 3 shifts a day, you did it. But that also meant when you got home after that test and you were exhausted, fine. You show up, but nobody's going to bug you about what time you arrived or what time you left or what you did at lunch or any of that. So it was a very professional, Hughes always got the job done. And I was really proud. I got hired to work on AMRAAM. So it was the original development of AMRAAM. Did all the wind tunnel testing for AMRAAM, created the aerodynamic modeling for AMRAAM, which was a completely new thing at the time. There was a guy there named Yoon Oh who had developed this mathematical approach to create a real-time aerodynamic model that could be interrogated by a 6DOF program, for example, using Fourier series and cubic splines. And it was just magical. It was really amazing. I applied that to AMRAAM and created the first digital aerodynamic model for AMRAAM. Before that time, the aerodynamic model was a binder full of graphs that you handed to the controls guys. At this point, we were handing them a digital model, and that had never been done before.
Wow.
So all those things that I hoped for when I went to work at Hughes happened. So understanding wind tunnel testing and performance analysis and aerodynamic model development and aerodynamics itself. Our department, the aerodynamic design department, was only about 50 people. We were working out in the San Fernando Valley in Canoga Park, and that was Missile Systems Group for Hughes Aircraft Company. That was about 3,000 people that worked there. So we're doing aerodynamics, propulsion, performance, stability and control, and ordnance in our department. There was a sister department right next to us that was doing all the mechanical design. So you'd think, wait a minute, what's left? You two departments of a total of about 100 people seem to be doing 90% of the missile. Well, the other, 2,800 people were doing all the electronics.
Okay.
And so the autopilots and the seekers and all of that stuff. And it took the majority of people who worked there to do those things. But that meant, it was like, I'm learning about all kinds of stuff. And I loved it. Absolutely loved it. Then Hughes had by far the gold standard for educational programs in the aerospace industry called the Hughes Fellowship, where it was almost like applying to go to university. You applied for the fellowship, and if you were selected, you could either go full-time or part-time to either a local or a distant university. So I had a really good friend at Hughes, who got chosen to go full-time. He went to MIT and got his Ph.D. I wanted to do the local part-time option, and went to the University of Southern California in the Aerospace Engineering department and worked through and eventually got my Ph.D. So it was a industry applied Ph.D. Some of the faculty at USC didn't like that. It was like, you should be doing,
fundamentals,
turbulence, which was a big topic at the time there. The department head was John Laufer, who was a big turbulence guy. Most of the faculty were in turbulence, not all. But I was in this high-speed CFD thing that very few of them understood at the time. That's another thing that Hughes gave me the opportunity to do, was essentially be in on not the ground floor of CFD, but almost just behind people like Jameson, right, who were on the ground floor, and learn all of the different computational simulation approaches that existed. So all the way from semi-empirical codes, which there were many of and still are some, to supersonic, hypersonic arbitrary body program that's been around since the 60s and the 70s, to the initial potential codes using CFD methods, and then eventually Euler codes and RANS codes. All of those things were just happening as I was at Hughes, and then also at USC. So it was the perfect time for that, and I just kind of absorbed as much as I could. There were lots of really great and very intelligent people at Hughes, and very gracious with their time and mentoring, and I just loved that. So I never regretted going to Hughes, and even years later, after I left Hughes, I went to Cal Poly as an academic. I received an AIAA award, and the AIAA president at the time was Malcolm Curry, who was the president and CEO of Hughes Aircraft Company. And I was sitting at the table with him, right, having lunch. And it turned out that I was sitting right next to him having lunch. And here I was, a Hughes fellow who had worked at Hughes, so worked for him, who left after he got his Ph.D. There was no requirements in the fellowship program of staying at the company after you graduated. Not 1 minute was required. And I asked him, so first of all, I told, okay, I was at Hughes and went to USC and got my Ph.D. and now I'm at Cal Poly. Why did you let me do that? And his answer was fantastic. He said, that happens probably to the majority of people who go through the Hughes Fellowship Program. But if you look at the upper echelons within Hughes Aircraft Company, of the managers and the directors, they're almost all Hughes Fellows. So we're creating the future direction of the company, the future leaders of the company through the fellowship program. And then what about the rest of you? Because what did you say you do? You're a professor at Cal Poly, teaching undergraduates and graduate students and telling them how much you love Hughes Aircraft Company.
Yeah.
What's wrong with that? That's a good thing.
Very smart.
So, yeah, it was amazing. So I really enjoyed that time at Hughes. I ended up being there a total of 8 years. After AMRAM, I worked on hypersonic IR&D projects. But then the possibility of going back to Cal Poly as an academic came up, and I applied for and got that job. And so I moved back up the coast to San Luis Obispo and became an academic, and started then to teach that aerodynamics course that I had
Oh,
taken
wow.
as a student.
Okay.
In fact, many of the faculty who had been there when I was an undergraduate were still there, including the guy who had taught me that course. I never told him that story. You know, you're a terrible teacher, but okay. And I hopefully did it better. I don't want to say anything bad about him, but I hope that I instilled in the students kind of an enjoyment and a love of learning about aerodynamics, because it's not a simple topic. When you come as an engineering student to university, maybe you grew up tinkering with cars, maybe you grew up doing electronics. You did not grow up doing fluid dynamics, probably. And so it's a whole new thing for most students. And it's something that typically is like you can't see. You can't hold a wrench and fix it. It's much more obscure. It's kind of hidden, but that also makes it kind of interesting. So that was a very long-winded answer, but all those things tied back to my uncle coming as a master sergeant and building me those models with me, and I've been doing it ever since.
Yeah, no, it's incredible. And also it's funny how your life takes you in certain directions, and you then sometimes come full circle. I mean, it sounds like you always had a love for the sort of Northern California, Santa Cruz, San Obispo area. I guess that was part of the desire to come back, is you'd sort of spent your time, as you said, in the place where, the rivalries were, and it was nice to come back. Did you miss that area, I guess, a little bit?
Oh, absolutely. So I would fly regularly up to San Francisco to see my parents, friends, while I lived in LA. So LA is an additional 3-hour drive south of San Luis Obispo, so that's a 6-hour drive
on a good day. Right.
From LA, from Western LA to Santa Cruz. That's a little bit too much, so I would fly up. In fact, San Francisco Los Angeles corridor is one of the busiest flight corridors in the world, and so there were lots of flights, and I would go up there quite a lot. That does not mean I hated LA the whole time I was there. I learned to love it to some extent. It's really funny in Los Angeles when somebody asks you, how far is it to that place? They will answer in time, not in distance, because distance is irrelevant. It only matters how long it takes you to drive there. It does not matter how far away it is. You get used to a whole different perspective on life. Certainly it takes a while to gear up to the fastness of the freeway system and life in general. It was completely normal for someone to call up and say, hey, we're going to Westwood to watch a movie, and not even think, that's 30 miles away and will take me 45 minutes to get there. So that's just normal. And so perspectives changed, but I was kind of glad to go back when I did.
I totally made that mistake recently. I was in Los Angeles, or in the area, thinking it's Los Angeles, it's like London, it's a city, you can just get across. And I had a meeting over in Agoura Hills, and I needed to get over to Orange County way.
Yeah, that's
and I thought,
awful.
I was stuck in a taxi for like 3.5 hours.
Oh, you took a taxi? Oh, my goodness.
I thought, how else do I do it? I mean, I don't think
drive.
there's a train.
Yeah. Everybody. Exactly. That's why everybody drives.
So, I was seeing it's quite a big distance. It's quite a big area.
It's crazy. It's 100 miles by 100 miles, the LA metropolitan area. And I worked with people at Hughes who lived, so we were in the West San Fernando Valley, very close to Agoura Hills. People who lived 2-hour drive in almost every direction from where we were. North, it couldn't be like southwest, because that would be the Pacific Ocean. West, east, people who lived all throughout that metropolitan area and commuted to work. I lived right next to our location, so I had like a 10-minute drive. There was no way I was ever going to do that. People driving for 1 to 2 hours each way, each day was insane, but that was normal.
Yeah, it's definitely a cultural thing, I guess. You just have to get used to it. It just becomes, that's why autonomous vehicles makes complete sense. Or eVTOL to, jump across.
There's one more step that's connected to all that. Shortly after I got to Cal Poly, again for the second time, I was started doing research with the people in NASA Ames Research Center up in the Bay Area.
Yeah.
So, and found myself being asked to apply to be a NRC postdoc at NASA Ames. And Cal Poly graciously allowed me to take leave and go do that. And so I spent 2 years up at NASA Ames. I call that the culmination of my CFD education to some extent. Although it never stops, it really took everything I had been doing up to that point and solidified it. When I first got to Ames, everybody in the chain of command, which that's not a word they use, but I'm at a military institution now, was a CFD researcher. I was in the applied CFD branch. The branch chief was Terry Holst, who had developed many full potential methods. The fluid dynamics division director was Paul Cutler. He was now overseeing both experimental and computational, but he was a CFD guy. And the Ames Research Center director was Bill Ballhaus, who also was a CFD researcher. And then as I walked down the hall, as I first got there, the names on the office doors were people all of them were people that I had studied as a graduate student at USC. I had read their papers. I had, there were multiple CFD branches. There was the basic, they just call it the CFD branch. That was the branch that Lomax started, had beam and warming and Tom Pulliam and all the people developing numerical methods. Tim Barth, they were in that branch. I was in the applied CFD branch, so that was Terry Holst, Joe Stager, Denny Chaussee, McCroskey, Gersian. It just goes on and on and on. And I was there to do research with Lou Schiff in the High Angle Attack Research Group, which also had some great people that I worked with. There were lots of students there in the summer. One of the people in our branch who was around in the summer was a guy named Eugene Tu, who was an intern from UC Berkeley. He was a student at Berkeley. He's now the NASA Ames Research Center director. So little Eugene is now big Eugene. And then I started having graduate students who would come up with me to do research. And it's a long list, but the first one was Ken G, and then Donovan Mathias, Scott Merman. Joseph Garcia. It just goes on and on and on. And many of them are still at Ames. In Donovan's the head of the NAS division, which is where the supercomputers are, which is where I worked.
You were in that building then?
I was in that building, yes. Building 258.
Yeah.
The meaning of NAS has changed over the years. When I was there, it was numerical aerodynamic simulation. And that's where I got my first supercomputer.
I didn't know
when I arrived, we had two Cray 2s.
Wow.
And they were named Navier and Stokes. And so, Jameson talks about that in his talk, that connection between the growth of the computer capability and the growth of the CFD. So if you go back from the 70s all the way back to like Merman and Cole in the early 70s doing transonic small disturbance CFD, where it was essentially 1D, and their results were just a graph. To then, as the computers grew, then you go to 2D. and to 3D, or you'd go from inviscid to viscous. So full potential came along, and Euler methods and Rand's methods, and then you would apply it to more and more complicated geometries. So airfoils, and then wings, and then full aircraft, as that capability developed. And that's when I was there, for a portion of that. I call it like the golden age of CFD at NASA Ames. It was amazing to be there and to take part in all that.
Yeah, it really seems almost everybody I speak to has some link to that NASA Ames NAS building.
Right.
I like the fact I did not know that the acronym changed.
It did.
Sorry, the acronym stayed the same, but the definition.
The meaning changed, yeah.
Yeah. But did you, I guess notable figures in CFD, who I believe, if you were there in the late 80s,
yep.
Did you ever come across Philippe Spallard? Was he there then?
Yeah.
Was that?
So he was at Stanford. There was a really close tie between NASA Ames and Stanford, as you might expect. It wasn't very far between the two. We were at Moffett Field, which was at the time a naval air station. It was great fun because P-3s would be taking off and landing all the time. And so there were always airplanes to watch. And then NASA had its own aircraft, so we'd go out and watch the launches of the U-2, for example, which is quite a unique thing to watch when it takes off. So lots of airplanes, and then lots of people who were grad students at Stanford. So Bob McCormick was at Stanford. He had been at Ames. Joe Stager had been at Stanford. He was at Ames and then later went to UC Davis. Just a lot of interbreeding, I guess you could say, between the two. And so we would go over to Stanford on a regular basis. For example, NASA had a really great educational program as well. So a lot of the grad students that I brought in from Cal Poly ended up going to Stanford and getting their Ph.D.s after they finished their research projects with their master's degrees. And so that was just a long line of people going that route.
Wow.
It was just I didn't know it at the time.
Yes.
But it was like you wanted to pinch yourself. I knew some of it, but you don't know. There's this whole layer of senior people who are very famous and well known.
Yeah.
But then there were all us quote unquote young guys. So Stu Rogers and Scott Lawrence doing hypersonic CFD, Tom Edwards. We not only worked together, we played together. So, for example, there was a NASA Ames CFD softball team. Tom Pulliam was on it. I was on it. Stu Rogers. All these guys were on the softball team. So we socialized as well. There was sort of like at Hughes again. Work hard, play hard. Was the name of the game. We played volleyball every day at lunch out on the lawn of Building 258, weather permitting. So there was a lot of fun going on as well. Many of us were San Francisco Giants fans, so we'd go up to Giants games up in San Francisco, and we didn't know who we were. Right? We didn't know. I didn't know that all these people would quote unquote grow up to become leaders in CFD for the rest of their careers.
Yeah, that's so nice. And I can't remember if I've said this before, but I really appreciate it. I was at Ames for a very brief time, and Tom Pulliam was very kind and, cycled with me through Palo Alto to find the place. And, there was that, I think maybe he epitomized that work hard, play hard mindset.
Absolutely.
He was always such a gentleman and a very, just Californian cool guy.
Tom was great. At some point, a few years after I was there, he got a major NASA award, not an Ames award, but a NASA award. And their award ceremony was black tie. You had to wear what you would call a dinner jacket, we call it tuxedo. And he got told over and over and over again, you will wear a tuxedo. So what does he do? He shows up at the award ceremony wearing a tuxedo and tennis shoes. So there was always that part of Tom that was like, I don't care. I will find a way to rebel. You just better hope that it's not too bad.
Yeah, that is funny. So one of the things so then you essentially were an academic, but an applied academic. You were interested in solving, real engineering problems.
Absolutely.
With CFD. One thing that, and I guess it's how I maybe got to know you a little bit, was the Oxford connection. How did that come about?
Yeah. So I had been at Ames, late 80s. I had grad students there all the way through the 90s. But I had my first sabbatical coming up. Being at Ames as a postdoc was not a sabbatical. I was just on a leave. And so I had started to look around many years before what were some good opportunities for doing a sabbatical. I really wanted it to be outside the U.S. if possible, and contacted quite a few people, not just in the UK, but at various places around the world. And one of those places was with the Oxford University Computing Lab, which was headed up at the time by Bill Morton, and included Mike Giles, among many other people. Ian Sobey was there. They had a very vibrant numerical methods group, a numerical analysis group that did CFD, especially Mike Giles. It was interesting. There were two parts to the computing lab at the time. There was the parallel computing group and then the numerical analysis group. The CFD was in numerical analysis. The parallel computing were the computer scientists. That organization, the computing lab, eventually split into two separate organizations. The computer scientists became the Oxford Computer Science Department, which is one of the premier computer science departments in the world. And the numerical analysis group became a group within the Maths Institute, which has since moved to very nice location in Oxford with fantastic. They were in a pretty crummy old building when I was there, but they're in a wonderful place now. So Mike Giles had a CFD group in collaboration with Rolls-Royce at the time, developing codes and applications for both Euler and RANS with and for Rolls-Royce. And again, I found myself in a place where people worked hard and played hard. Although when I first got there was some culture shock. I'd been going to England since I was a teenager, so there was no general culture shock, but there was a workplace culture shock in that there was this very structured workday. You started at 9, and at 10:30, there was a coffee break. And it wasn't optional. If you sat there, they would come get you and say, come on down to the break room, to the tea room, and get your biscuit and have some coffee or tea.
So English.
You had to go. All right. And that lasted about a half an hour. And then so from 11 to about 12 or 1, you'd work some more. And then it was lunch. We had a great kind of tradition. We would try to take the CFD guys together for lunch to our colleges, the colleges we were at. So we would experience the different colleges. So, for example, one of the guys was at Katz, which is a very modern college by Oxford standards. And so, what was it like being a grad student there at St. Catherine's? compared to I was at St. John's.
Oh, wow.
What huge difference. But then a lot of hard work and great things getting done. But my point during the workday was, well, then there was an afternoon tea break as well. And I felt like when I first got there, how does anybody get anything done? You're constantly taking breaks throughout the day. And then I realized, first, during the breaks, while we weren't officially working, we were working. That's when people's frustrations would come out. I've got this thing and it's not working, and invariably somebody else there would say, oh, I know how to fix that. Yeah. So you got work done, even though we were having this social event called a tea break. Yeah. And that just continued the whole time I was there. So I came for a half-year sabbatical in 1995, came back the summers of 96 and 97. I learned that from Gil Strang. Gil Strang was a constant visitor to the numerical analysis group. He, of course, the very famous numerical methods professor at MIT, who only recently retired. He kept teaching well into his 80s. Wow. And he taught me that it was very enjoyable to spend your summer in Oxford. Oh, yeah. And that no matter where you worked, during the regular part of the academic calendar, you might want to find a way to be in Oxford at the summer. And I have taken his advice. I skipping to the present time, I'm going there in just a few days. Yeah. No longer with the numerical analysis group, but with the hypersonics team there. I was there last summer for probably 6 weeks. I'll be there this summer for about 4 weeks, and hopefully that continues. But anyway, back to Mike Giles. Mike was wonderful. He was English, but he'd gone to MIT to get his Ph.D. He had stayed there and worked on coding and aerodynamics for many years. Brought that back with him to Oxford. Had this vibrant research group while I was there, and then later after that. Then he started to go off into computational finance, but also big time proponent of GPUs from the very beginning. Yeah. From the very beginning. So if you go on his website, there's all kinds of information that he had developed about GPUs, how to use them, how to understand how they work. It's all just freely available. He just posted everything. And so Mike and I have kept in touch off and on through the years. He recently became the professor of numerical analysis in the Mass Institute, which meant he got moved to Balliol College. That's Bill Morton's old position at Balliol. And was named a fellow of the Royal Society just about a month or two ago, when their announcements came out. So Mike's still there and heading up all numerical analysis in the Mass Institute and doing wonderful, wonderful things.
Yeah, I can just very jealous, and also I think it's an amazing time that you had those, the 90s and the Oxford colleges. I mean, now people make movies about this, don't they?
Exactly.
It's like an American thing, isn't it? It's quite popular in America. This coming to England for the summer, and you lived it. You had that.
That friend of mine who went to MIT to get his PhD when we were at Hughes came to visit while I was there and said, "This is your graduate school experience," because I had been kind of part-time at USC. He said, "This is your real graduate student experience." The MCR, the Middle Common Room, graduate students at St. John's adopted me, even though I wasn't there as a student. I was there as a visiting academic. So the distance from the computing lab to my room at St. John's was about a 5-minute walk. Great commute.
Yeah.
Invariably, I would leave the lab and be walking back to my room, and somebody from the MCR at St. John's would invite me to something that night. because I would just see them as I was walking. Maybe I'd go to my pigeonhole in the college, front rooms and check my mail, and I would see somebody. And there was a barbecue, or there was, we're going out for a bike ride, or whatever it was. I probably, those initial 6 months, only spent 4 or 5 evenings alone at Oxford. Most of the nights, something came up and just got grabbed and brought into that lifestyle at Oxford. So you're right. It was like you were in a movie. I was there, like I said, last summer, and I noticed something that was kind of tragic. I was texting my wife, who I happened to meet at St. John's as well.
Okay.
Had to go to England to meet somebody from Kansas. That I didn't see the grad students hanging out doing things in the college. And she texted back one word, cell phones. And she was completely right. There, none of those things that happened to me when I was there were going on. I even talked to some of the MCR members and asked, do you guys do activities together? Do you go, like we would go to Stratford and go see a Shakespeare play, or we'd go to London and see a play, or we did things all the time. I remember going to Bournemouth once for a bike ride,
Wow,
which was kind of crazy and fun and all kinds of things. None of those things were happening last year because everyone's friends, relations were through their phone and not through the person I lived next to.
Yeah,
and
interesting.
That's sad, because we both in the lab and in the college were very close, and I really enjoyed that.
Yeah, it really is incredible, and I guess having that. I'm a strong believer in this, experiencing the different cultures of academia and industry, and different academia and different industry gives you a more rounded, appreciation, which I assume has been very useful for you as you collaborate with different groups around the world.
I didn't realize it at the time, but I was just collecting relationships. And when I look back through my career, that's what I remember. And I still have those relationships, and I still interact with those people all the way back to my Hughes days, and even, as an undergrad at Cal Poly. By taking advantage of those situations, it was just kind of magical. I loved it.
Yeah, that's incredible.
And of course, you're learning about CFD, and we were doing drag extraction from CFD solutions. That's what Mike and I were working on. Could you predict drag using a RANS code? How well could you do it? And so we were working on that while I was there. That was something Rolls-Royce was interested in as well. And so that those are the kinds of things that I was doing when I was there in the 90s. Now I'm there working primarily in hypersonics, but that's another whole tale of how that happened. But certainly felt like I was just constantly learning and growing in because I was taking advantages of these opportunities, and not everybody does that. Later in life, I spent 3 years living in London. So eventually I left Cal Poly and went to the Air Force Academy. One of the things that came out of that was I got to do an exchange to the AFOSR office in London. I spent 3 years as a tech director, and then through that met academics all over Europe and the UK and Australia. I was funding hypersonics research for Europe and Australia. And so got in on sort of the ground floor of what was going on at Oxford with Matt McGilvray and his team. And we were one of the first organizations to fund research with Matt and his hypersonics group. There's a famous story at the AFOSR office in London. It's called EORD, the European Office of Aerospace Research and Development. we've actually, in that office over the years, funded a few Nobel Prize winners. And the great story is there was a program officer back around 2010 or so, 2009 maybe, who funded a fledgling research project at the University of Manchester about this weird thing called graphene. And the guys who had that project, and this was one of their first funded projects for their graphene project, for their lab, ended up winning the Nobel Prize I think it was in chemistry, and invited that program officer to the Nobel ceremony.
Wow.
Because he was the first one. Now they've got this massive building at the University of Manchester and tens of millions of dollars of research going on, but they still remembered back. That's how we started. And I think Matt McGilvray and Peter Ireland and the people at the Thermofluids Institute at Oxford felt that way about AFRL and AFOSR, and not just me, but others as well, having faith in them and supporting them and helping them to get started as they were putting together tunnels and developing capabilities in CFD, et cetera. So that was a wonderful way to make that connection while I was officially working as an academic at the Air Force Academy.
Yeah. Well, one of the things we wanted to pivot to a little bit was around hypersonics. But as a link to that, how did you start to get into that? What made you then go to the Air Force and today, I guess, mainly focus on hypersonics? How did that transition come about?
So it was there back at Hughes. Mm-hmm. So way back in the 80s with the R&D projects I worked on. But there were no tools like we have today back then. So I was actually using the supersonic hypersonic arbitrary body program to analyze aerodynamic shapes, which is just surface impact methods. So Newtonian, modified Newtonian, tangent wedge, tangent cone methods applied to geometries. But then when I went back to Cal Poly, there was very little hypersonics going on. And that leads to an important, if you don't understand this about hypersonics, especially in the US, you don't understand it, that hypersonics has been very cyclical since the 50s and the 60s. The funding, if you graph it versus time, is a sine wave. And the period of that sine wave is about 10 to 12 years. And that's big projects like, the Space Shuttle coming and going, or Apollo coming and going, or the National Aerospace Plane coming and going. And in between those major peaks were these massive valleys. and that meant that I always say you couldn't plan it better to ruin progress than to have 10 to 12 years between the peaks. Because that meant halfway between, everybody who had done that peak was gone, or almost everybody. The people left maybe with a bad taste in their mouth about hypersonics. The facilities fell into disrepair, perhaps, and or were mothballed, or even in many cases destroyed. There's a report from 1963 that there were 78 hypersonic wind tunnel facilities in the United States at that time. By about 2015, there were about 35. 78 to 35.
Wow.
And it's those cycles that led to that. There were many hypersonic tunnels in aerospace companies back in the 60s, and there was only like one or two left by 2015 or so. So those peaks and valleys really hampered progress in hypersonics in general, certainly hypersonic CFD, because it wasn't a thing, right? The space shuttle was designed with no CFD. None. Now, people later on did lots of CFD for return to flight and different things like that. but there wasn't any. The things that you expect to happen over time and were happening for CFD weren't happening for hypersonic CFD and hypersonics in general. I like to, this is one of the things I love to talk about this history to my students, because I think, when you go out there in your careers, you're going to wonder, well, why is hypersonics so far behind every other part of aerospace and aerodynamics and CFD? In 1992, Bill Clinton ran for president, and his campaign manager was this very colorful guy named James Carville. I don't know if you've heard of him. If you look him up on YouTube, he has this thick Southern accent, and you begin to wonder about his intelligence, perhaps. That's a common bias in the United States. But he's a smart guy, but he's also a little wild and wacky. During the campaign, he put up on the campaign headquarters wall a sign that said, "It's the economy, stupid." He did that to remind everybody who worked there and Clinton, stay to this point. If you don't understand this and stick to this, we're going to lose. If you stick to this, we have a chance to win. So what I tell my students is, I'm going to use that phrase, but just change one word. Hypersonics, it's the heat, stupid. If you don't understand that, then you don't understand hypersonics and everything about the challenges in hypersonics. And that has to do with experimental testing, with flight testing, and with CFD, revolves around that huge heat that has to be dealt with on the vehicles. I like to explain that to my students just by using, going to their normal shock tables. And if you're at Mach 2, look up the temperature change across a normal shock, and it's, okay, it's going up, but it's not going up that much. But if you go up to Mach 5 and Mach 10 and Mach 15, it goes through the roof. It's exponential. And that's all contained within the kinetic energy of the free stream. That's huge amount of energy in the free stream that then dissipates over a shock in a very small distance to what? You go from Mach 20 to Mach 0.5 within the thickness of a shock. What happened to all that kinetic energy? It went into heat. It went into pressure work and other things as well, but it went into heat. And where did that heat go? It's trying to go into your vehicle. It's also trying to change the chemistry of the air going around the vehicle. It's affecting everything. It's absolutely affecting everything. And so you need to understand that. And that, along with the cyclical nature of funding in hypersonics, essentially meant hypersonic CFD just wasn't a thing. There were very few people doing that. When the National Aerospace Plane came along, for example, the National Aerospace Plane started in the early 80s. It was canceled in 92. I keep with me this report on the Defense Science Board report on the National Aerospace Plane program because it has an interesting list of issues that needed to be invested in and improved before we would start a new national aerospace plane. So this is kind of like, what happened? What happened here? Why did we go from a DARPA design in the early 80s that was like 50,000 pounds and had 2.5% payload, which is pretty good for hypersonics, not good for subsonics, but pretty good for hypersonics, to a 500,000 pound nearly vehicle in 92, the X-30, it's right there, that had no payload, zero payload, because of the heat. They couldn't close the design. It just kept getting bigger and bigger and bigger. So the Defense Science Board, kind of post-mortem of the National Aerospace Plane, called out a list of things that needed to be invested in order to improve the next hypersonic vehicle development. A lot of the things on that list are just like you would be able to guess. One of them was, well, you need to better define what the application of this vehicle is, not just some esoteric, let's do it. What is it for? What's it going to do? But then they had a long list of things that needed to be improved. So structures, materials, those make sense because dealing with the heat. Propulsion system, so it was an air breather. You needed a scramjet, and they never got a working scramjet design for NASP, really. And they had concepts, but it just never got there. Aerodynamics, okay, aerothermodynamics. And then, really, really strange, on this bulleted list of things that needed to be invested in was CFD. Was like, which one of these things is different than the others? You know, yeah. Structures and materials and aerodynamics and propulsion are all typical aircraft disciplines, right? CFD is not that. It is something you use to do predictions with and simulations. And they went like nuts on CFD wasn't ready for prime time. Hypersonic CFD. Why? Okay, they just made the list. Turbulence models. Almost all turbulence models were developed using low-speed wind tunnel data. Yeah. Not subsonic wind tunnel data. Yeah. Like water tunnel data or 10 meters per second wind tunnel data. And then what happens? You put that in a CFD code that's being developed for subsonic or transonic aircraft, and it's like, well, can I use it at Mach 6? Yeah, you can put in Mach 6 and some altitude and get an answer. And I heard Graham Candler say this once. I'm sure the people who developed those turbulence models never in their wildest dreams thought someone would use it at hypersonic speeds. Yeah. But that's what happened. Yeah. Perhaps with a compressibility correction, but that's it. And then transition prediction, you could say on the list of things that killed NASP, transition was probably up there with them. The inability to predict transition on a flight vehicle was almost notorious. Dennis Bushnell at NASA Langley used to say, we've been, singularly unsuccessful at predicting transition on just about everything that's flown hypersonically. And then he added, or even supersonically. Yeah. The X-15 was an example where the wind tunnel test said the flow is going to be mostly laminar while they're flying, and they come back, and of course the flow was turbulent. Well, that's okay. That if you just think about transition and turbulence from a subsonic perspective, it's like, okay, you have more drag. Yes. You also have 3 to 8 times more heat transfer in a turbulent boundary layer at hypersonic speeds than in a laminar boundary layer. That can kill your design right there. Yeah. Because what are you going to do as an engineer if I don't know, is it laminar or turbulent? And if it's turbulent, it's 3 to 8 times more heat transfer, which means I have to have the thermal protection system, maybe active systems that are on board and doing work, like on the X-51, cooling systems, etc. That could mean I have no payload. And that's what happened to NASP. No payload. And so transition was a big deal. And there were others. So then you talk about the thermochemistry and its impact on turbulence. So as you go through that normal shock, the temperatures can go up to easily 4,000 Kelvin, 6,000 Kelvin, 10,000 Kelvin, depending on the Mach number. And now you have chemical reactions taking place due to dissociation and ionization and all kinds of things. Where's that modeled in your CFD code, your transonic CFD code? It's not. It's not there. You at best have, well, okay, I choose perfect gas law. Okay. And I choose gamma. And that's it. That is it. So there's all these traps for using that CFD code that was developed for subsonic transonic flow, but using it at hypersonic speeds. It doesn't usually work.
No.
It just doesn't. And as a designer, then, you become conservative. Engineers are typically conservative when it comes to design choices and uncertainty. And if you don't know, you're going to assume worst case. Well, the worst case assumption can kill your design. That is, assuming that the flow is fully turbulent along the entire length of the vehicle. And now you're in deep trouble. So those things make hypersonic CFD difficult. They also make hypersonic ground testing difficult. They also make hypersonic flight testing difficult. I mean, I was at Oxford last summer and they were showing one of the SpaceX launches, and one of the grad students said, what's happening right there? I go, well, that's the fin burning off. And they're all cheering, because they don't even know what's happening. And it turned out to be true. So it impacts everything you do in hypersonic. So ground test facilities typically, to get that high of Mach number and that kinetic energy, can only run for milliseconds or hundreds of milliseconds. The flight tests have all kinds of issues, often to do with the heat. That also is like, it rolls back on itself, because now I don't have validation data that I know is good for flight test vehicles. So what's going on when I want to validate my code and I don't even know what the truth is? I don't even know, did that tweak I just made to the turbulence model, specifically for hypersonics, for example, make it better or worse? I don't even know. Yeah. And so all of that hampered the development of hypersonic CFD, while there was lots of effort being placed in transonic CFD. In fact, I like to say that if you look at the typical numerical methods developed in the 70s and the 80s, so now we're talking about Jameson and all these guys that I worked with at Ames, whether they thought about it explicitly or not, were developed for a normal shock in a cell, right? And so the upwinding approaches and, Mermin and Coles just, having the switch between elliptic and hyperbolic and all of that was based on this picture in your mind that that's what you were dealing with. Now I'm going hypersonic. The shock's not normal. Maybe a little portion of it is. It's highly swept. Is that transonic numerical method working for my hypersonic flight conditions? Does it know what to do when the shock is like swept back at a Mach angle of 25 degrees? So it's not just the physical models. It's not just the chemistry. It's not just turbulence and transition. It's even the numerical methods. There has been no investment whatsoever in developing hypersonic numerical methods for CFD codes. Zero. And part of the problem there has just been, everybody kind of pointing at everybody else. Yeah. So, the DoD says, well, that's the company's job. There is no appetite in an aerospace company these days to spend money developing a CFD code. Zero. Because why? They did that back in the 70s and the 80s and developed in-house codes like Boeing and Lockheed Martin that they've been improving and using ever since. For a fighter or a cargo airplane. Now you use it on a reentry vehicle and it doesn't work. How do you deal with that? They're not going to spend money developing hypersonic CFD. The government doesn't spend money doing that. Very little physical modeling research is done. lots of basic science research in turbulence and transition for hypersonics. Almost none of that going applied, right? Where you take what you've learned and then make a model out of it. Not only wasn't that done, nobody even funded to ask those questions. What would I have to do to make that happen? Just wasn't happening.
So I guess maybe this tees up then the question.
It sort of does.
I like what you did there. The HVSI program, maybe Hypersonic Vehicle Simulation Institute.
Yeah.
Maybe you could explain a little bit about that program, what that.
Right.
Yeah.
So after Cal Poly, I came to the Air Force Academy. It had a great group of people doing CFD, Scott Morton, Doug Blake, Jim Forsyth. I joined with them doing massively separated flows, so high angle of attack flows, which I had done when I was at Ames. So that was a nice connection. What then pushed me into hypersonics was the discipline director for aerodynamics at the Air Force Academy at the time was John Burton. And John Burton had spent his career working in hypersonics. He asked me to become the co-author of his textbook called Aerodynamics for Engineers. By the way, just by accident, the 7th edition, published by Cambridge Press, just came out this week.
Classic.
I just got my copies last Friday. And so that was not a shameless plug. It was just, I'm kind of proud about that because it takes years. Yeah. It takes years, and it's just kind of magical. John Burton not only asked me to help him with that, but also was heavily involved in doing hypersonic research at the Academy, both experimental. And then he was not a CFD guy, but asked me to be his connection to, well, what could different simulation approaches do for these projects I'm working on? And he went all the way back to the Apollo days at NASA Johnson. And he worked for also Sandia, and then was a professor for many years at the University of Texas at Austin before he came to the Air Force Academy. He wrote one of the two probably best used textbooks on hypersonic aerothermodynamics, along with John Anderson has a book, and John Burton has a book. And so that's what started to get me ramped up doing hypersonics. Like I said, I went to London for 3 years, working as the tech director there, and that experience, so being a program officer as well, funding research at universities in hypersonics, led me, when I returned, to be asked to start the Hypersonic Vehicle Simulation Institute for the DoD High Performance Computing Modernization Program. They fund the development of institutes, realized that hypersonic CFD was going to be an important thing and that it was not being invested in. And so they wanted me to determine what needed to be invested in, which led me to spend many hours on telephone interviews with people, the aerospace companies and government labs, and find out, well, where were these shortfalls? What were these issues? And what do you need to do a better job? I was kind of surprised that none of that had taken place. Nobody had ever asked those questions before, at least not that I knew of. I kept pinching myself saying, how can I be the only person asking these questions about hypersonic CFD? Certainly people like Graham Candler and his gang at Minnesota and other places knew that this was a problem. But who was going to fund research in that area? Applied research, not basic science research. And so started funding research in physical model development, and also validation data. So the collection of data that could be used. So for example, at Oxford, they're doing a double cone experiment. They've been doing it for quite a few years. They've got another test coming up in T5 in Queensland. They're all over in Australia right now for a conference. And so, just so many questions. I mean, that came out of the 2013, 2014 AIAA hypersonic CFD blind code study, At Kubrick, they did some tests on a variety of basic geometries, like the Hall cylinder and a double cone and a cone flare, and asked for people to submit their simulations. And then at an AIAA meeting in 2014, showed the results, and they were terrible. They were terrible. Not for all cases, not for all geometries, but in general, it only led to more questions than answers. That did not transcend into funding for trying to accomplish any of those things. So I felt like that's what HVSI was starting to do. Since then, ONR, Eric Marino, has picked up on that, and he's really become kind of a great supporter of that. AFOSR, not so much, because they only fund basic science. So developing, turbulence models is not in their ballpark. But it's in somebody's ballpark. I just couldn't find out who. And so that led to quite a few years of trying to not only determine what the issues were, but then trying to fund applied research that could help solve them.
And that is across, I guess, academia. How about industry? What's the involvement with industry? Are they co-funding or sponsoring, or is this? Yeah, how do you? Yeah.
So first, they were the people I was asking the questions to, but then kind of a fun thing happened almost by accident. As I would fund these projects, people from industry asked if they could participate, not paid, but just as consultants on these university projects. So, for example, I had 2 transition modeling projects, one at the University of Arizona and New Mexico State, and one at the University of Tennessee, later Penn State, and Texas A&M. And each of those projects had industry partners who were giving advice, looking what are they doing and how is it working, and maybe we can use this. So Raytheon at the University of Arizona and Lockheed Martin with the one at Tennessee, and just being there side by side to be involved. But again, they're not going to get any money to do that on their own. When they get a program like a new hypersonic vehicle, there is zero money for developing tool capabilities. It's all about getting answers and using whatever you have and trying to get to where you need it to get. And so they really realized the importance of that. I had somebody at Raytheon tell me, this is the first time when the government came to me and asked me questions, and then I realized they actually listened and did what I recommended for them to do. And so that was kind of a proud moment that they realized we were trying to do what needed to be done.
Now, this you mentioned the context of the high performance computing modernization program.
Yeah.
One of the questions, I guess, is on most people's lips, broader than just hypersonics, but I want to ask you about the hypersonics, is the role of AI. As you say, for decades, turbulence models and transition models were done using empirical or semi-empirical methods. Are you optimistic, skeptical? Yeah, what's your... It's a hot topic and very opinionated, I find, so I'm interested to see your view on this.
So AI and or machine learning for some aerodynamic, increase in our capabilities and our knowledge, I think will work. I'm not so positive about it working well for hypersonics. And that backs up to what I said about the lack of validation data. AI and machine learning have to have information, right? They have to know, hopefully, mostly, within some error bar, what the truth is. And we don't necessarily know that. And or the things that we have learned historically might be classified. And so they can't have it.
Yeah.
And so the first question I ask when somebody recommends doing some kind of AI machine learning hypersonic physical model development is where are you going to get your data? How is that process going to work when your data is very slim or next to none? And I mean, Steve Schneider at Purdue can probably go through every hypersonic wind tunnel test that's ever been done and tell you all the problems that happened in that test or with that data, especially if it relates to transition. There are always questions about the tests, and flight tests too. And so how is it going to work? Because it doesn't know what the truth is or even what approximate truth is. So I'm kind of skeptical. I think you could use DNS simulations of hypersonic flows to maybe help that. There's some great people working on that. Certainly Graham Candler and others around the world. So you could say, well, let's start simple, some simple flows, some very expensive. I mean, Graham Candler likes to say, you give me 1 billion grid points and the computers to solve my code on, and I can tell you what's happening, and I believe him. That's just not helpful for a design approach, other than answering a specific question here or there, and that can absolutely happen in the development of a program or of a vehicle. But it's not how you're going to do the design. You can't afford that as the way to predict your aerodynamic database, for example, for a vehicle. So I'm skeptical.
Yeah, no, that's interesting. And I think I understand where you're coming from. I guess the analogy with the lower speed is that over the past decades, there has been quite a lot of data. There's no issue of classification. There is still an issue of data being truly public, but
correct.
There is an ability to generate that data. And crucially, the experimental data and the flight data is relatively mature. I guess with hypersonics, we're maybe too early on. Like, if CFD and experiments get better and better, but then I guess you still have the classification issue, and it's still a more niche problem than low speed flows. Right.
So it has lots of limitations that may make that something that's not ready for prime time for quite a few years.
Yeah. Well, it's good for people in CFD jobs, right? It keeps them.
That's right.
If there was a solution with AI right now, then we'd all retire.
When I first went to work at Hughes, I at one point, maybe during my first year, and the entire first year, I felt like I was an idiot because everything I did was wrong. Somebody said, "Don't ever complain about how hard this is, because turbulence is going to pay your paycheck for the rest of your life." And that's certainly been true.
Yeah. Well, you know this, that people often in experimental testing will say, for the past 40 years, CFD has claimed to replace wind tunnels, and they're still going.
Well,
so
I am a strong believer in the opposite opinion. I think CFD and wind tunnels and flight tests should be in a symbiotic relationship, that they can inform each other. You can learn about things from the test using CFD. I think they should be done in parallel. I don't think it should be, we ran an experiment and now we have to figure out why it didn't work. So let's use some CFD. No, you should be designing the test with CFD. You should be doing the simulations at the same time you're running the code. I mean, I had a great experience when I was at Ames working on the high angle of attack research vehicle, the F-18, flying at very high angles of attack. They were doing flight tests and wind tunnel tests for that. So we had all three legs of the 3-leg stool. And I did CFD simulations of what the pressure distribution would be on the F-18 for a certain flight condition, and sent it down to NASA Dryden. And then they did the flight tests and sent back the comparisons. And I was like, wow. I mean, very few grid points at the time, cells, whatever, relatively speaking, compared to today. Yet we were pretty much nailing those, especially at high angle of attack, where you get flow separation and vortices and everything else, with RANS codes using algebraic turbulence models with corrections for high angle of attack that Degani and Schiff did. We were doing a really good job. And I had predicted that before the flight test. That was a great feeling, a true prediction. And then comparison with flight test data. That doesn't happen, but I think it should be happening all the time.
Well, someone told me this, and I can't remember who it was now, but they were commenting that part of the issue is maybe previously, when CFD was less mature, for whatever reasons, people would often do an experiment and CFD. They would be doing both. So they would naturally, where now, because the fields have grown and expanded, very few people do the CFD and the experiment themselves, do they? They tend to be siloed into an experimental person or a CFD. So maybe that makes them separate, if you know what I mean.
So I think that's a mistake. I think when you're doing experiments, you should have, maybe they're not in your research group, but they're in your organization or your lab. People doing CFD, they're doing that at Oxford. So you've got Matt and Luca Damara running the CFD group. Now he came from Imperial College and is at Oxford doing a great job. Matt's done marvels with the experimental facilities. He's got a whole army, not only of regular graduate students, but we send graduates from the Air Force Academy there on a regular basis to get their degrees, their graduate degrees. And so I think that's essential. I mean, that's one of the things I'll be working on this summer is comparing for a reflected shock tube the conditions with CFD and with from the tunnel itself, the operation of the tunnel itself. To then understand, well, what are the conditions in the test section? You think that would be a simple question, right? If I'm down in the low-speed tunnel in the aeronautics lab here at the Academy, I don't ask, what is the Mach number in the test section? Or the Reynolds number. I don't ask that question. But you have to ask that question when you're doing hypersonic ground testing. And how you answer that question could mean your results are it's not your results are bad. You've collected good data, but you don't know the conditions that data is for. So when you report it, you say this is for a Mach number and a Reynolds number of such and such. Oh, how did you get that? And nobody or very few people ever say that in their papers. Okay, I've got a Mach 6 Ludwig tube, and I can do some measurements, and I can tell you that it's 5.93, and that's pretty typical. And but what's the Reynolds number? How do I know the Reynolds number? What do I have to measure to figure that out? And in a test that lasts for a millisecond. So those are really interesting things that I'm still learning from and having enjoyment in doing.
Yeah. Well, our time is nearly up. I appreciate we could probably talk for hours on this, and it would be great to have that opportunity. But one last question I had for you was, you've worked in the aeronautics industry, both in academia, now industry, government. What advice would you give to people who are maybe your younger self, who are looking for a career to follow you? What advice would you give them?
So, because I was involved in student activities at AIAA for many years, I've had people ask that question before. What's the thing that led to all this? Well, first of all, I didn't plan any of this, but I would say, in one word, perseverance. Don't give up. So I think back to that kid coming out of high school who was being told you're making the worst decision of your life. And all I could say was, I love airplanes. I'm going to do this because I love airplanes. And if it means I have a career where it's up and down and bumpy, and it was for many people, that's fine. But it hasn't been for me. Just don't give up. If this is something you really enjoy, like they say, you'll never work a day in your life. You'll be enjoying what you do. You'll be learning. You'll be teaching. You'll be helping others to understand. You'll be writing textbooks. Whoever thought when I was taking that aerodynamics class as an undergraduate that not only would I teach aerodynamics, but I would write the textbook. It's like, that's crazy talk. Yeah. Just keep going. Do what's interesting. Do what you're interested in and you enjoy, and don't necessarily listen to what everybody else is saying. I remember Dustin Hoffman in what's that movie where the guy comes up to him and says, "The future is plastics," right? That was a famous line back. That was in the early 70s. The future is plastics. It's like, all right, do I really want to listen to a guy who told me that at a party when I graduated? No. Do what you really are interested in, and don't let other people. You want to grow, you want to expand, you want to evolve, but just keep going. I saw many people along the path who were, I absolutely believe this, much smarter than I am, who crashed and burned on the side of the road for whatever reason. I was not the instant, I figured it out, I understand it, I know what I'm doing person as I went through my studies. And maybe that helped because I was just going, I have to work. I have to spend time. I have to try to understand this, and I'm going to put that time in and get that done. And then, like I said, couple that with meeting people as you go, and not just at that moment, but making those relationships, the relationships of a lifetime, because those people aren't just colleagues, they're friends. Yeah. And there's hundreds of them. My kids always, Dad, you don't have any friends. I go, no, I have friends all over the world. It's just, I go to Oxford and they're there. I go to Germany to DLR and they're there. Or I go to Australia and they're there. It really is more than just the thing you're doing. And we said that for Hughes and for Oxford and, all the way through. Just enjoy it and you'll make it work.
Yeah. Great piece of advice. I completely agree with you. Perseverance and doing a job that you love and you're passionate about makes it feel less like a job. Of course, there's always times when it will feel like a job and there'll be stresses and everything. But if you love what you do, then it makes it all a lot easier. So, yeah, thank you again. This was, really, I learned a lot, and I love your life story and obviously there's so many things that you've done, more in the specifics, which we didn't get time. We kept this a little bit more high level, but I will put some links to, the textbooks and papers and things that you've done so people can, investigate in their own time. But yeah, thank you again, Russ. This was great.
My absolute pleasure, and thank you, Neil, for doing this, for not just for this podcast, but for all the ones you've done. They're really interesting, and I've enjoyed watching them.
Great. Thank you.